So the first thing we're going to talk about is what is a mole. And in chemistry, a mole is a very useful number. Now, to help you think about what a mole is, think about the word dozen. A dozen means 12 of something, right? So that word dozen just is a number. The same thing with a mole. So like, for example, when we say there's 1 dozen of something, we mean that there's 12 of that thing. So in the same way, when we say there's 1 mole of something, we say that there is 6.02 times 10 to the 23rd of that thing. Now don't let this number scare you. It's just exactly like 12. It's just a number. The reason why it's odd 6.02, and actually there's some more digits after this, and why this number is times 10 to the 23rd, we won't get into. We just have to know that a mole is a number. To get you a good sense of what times 10 to the 23rd is, think about what 10 to the 6 means. That's a million, right? What does 10 to the 9 mean? That's a billion. So this is much, much, much greater than that. So the mole is a very, very large number. And this number has a special name. It's called Avogadro's number. Okay, so let's apply this new concept of the mole. So for example, when I say I have a mole of sulfur, if I have a mole of sulfur atoms, that means I have 6.02 times 10 to the 23rd atoms of sulfur, right? Same thing if I say I have a mole of, let's say, of a molecule like carbon dioxide, CO2, then I also have 6.02 times 10 to the 23rd molecules of CO2, right? It doesn't matter if it's an atom or a molecule. So for example, if I say I have a mole of students, then that means I have 6.02 times 10 to the 23rd of students. So it's such a very, very, very large number. And so what do you recognize here? That this is an equality, right? So if this is an inequality, then we can use it as a conversion factor. So for example, if I were to ask you to convert from moles into atoms, then you could use this equality. Or if I ask you to convert atoms into moles, you can also use this equality. Right? It's almost like saying if I have 6 eggs, how many dozens do I have? You would say you have half a dozen. Or if I said you have 2 dozens of eggs, how many eggs do you have? You would say that's 24 eggs. Kind of the same thing, right? That definition of dozen can help you translate into the number of things that you have. Okay, so let's start with this example. If I ask you how many sulfur atoms there are in 0.02 moles of sulfur, so if you have 0.20 mole of sulfur, remember you're going to multiply using the Avogadro's number. And Avogadro's number says there's 1 mole of sulfur. Oh, by the way, moles, we abbreviate as MOL sometimes. We drop the E. That's how we roll. So back to here. So 1 mole of sulfur is 6.02 times 10 to the 23rd atoms of sulfur. So you do that math. That's 0.2 times 6.02 times 10 to the 23rd, which turns out to be 1.204 times 10 to the 23rd atoms of sulfur. Again, talking about sig figs here, we have 2 sig figs here, so our answer should only be to 1.2. Right? Let's do another example. So the next example is how many molecules of CO2 is in 0.2 moles of carbon dioxide. Okay, so again, we start out with the fact that we have 0.20 moles of carbon dioxide, and we know that for every 1 mole of carbon dioxide, there is 6.02 times 10 to the 23rd molecules of carbon dioxide. Do this math, and we should get, were you able to guess? Yes, it's in the same number, right? 1.2 times 10 to the 23rd molecules carbon dioxide. it makes sense that it's the same number, right? Because we're just talking about 0.2 moles of that same thing. So the number is 0.2 is the same number as the 0.20 moles of sulfur that we just did. So think about that to see if it actually makes sense for you. So the reason why we have to use the mole in chemistry, remember, which is a very large number, is because in chemistry we deal with atoms. And what do we know about atoms? They're very, very tiny, right? So we need a very large number to help us deal with these very, very small things. What I mean by that is, for example, if I were to ask what does 1 mole of sulfur atoms look like, this is what 1 mole of sulfur atoms look like. If I say what is 1 mole of iron looks like, that's what 1 mole of iron looks like. Right? So you can fit these things in a beaker, and in that one beaker, there's 6.02 times 10 to the 23rd power atoms of sulfur, of iron, so on and so forth. Okay? Notice as we go across this list here that 1 mole of something becomes larger and larger. Right? 1 mole of sulfur, compare that to 1 mole of sugar. That is 1 mole of sugar. Why do you think 1 mole of sugar looks so much greater than 1 mole of sulfur? Sulfur is just 1 atom, whereas sugar is composed of 12 carbons, 22 hydrogens, 11 oxygens. So it's a much bigger molecule. So if you have a mole of that, then it's going to be taking up more space. It's going to be more massive also. That's the same thing as saying you have a dozen of marbles, tiny marbles, versus a dozen of a bowling ball. They're both dozens. They're both 12 of them, but a dozen of a marble, would be this much. A dozen of bowling balls would be about this big, right? It's larger. So let's try, for example, look at carbon dioxide. That's a simple case, right? CO2. For every 1 of carbon, there's 2 of oxygen. So if I say I have 1 molecule of carbon dioxide, you say you have 1 atom of carbon and 2 atoms of oxygen. Now, what if I said I had 2 molecules of carbon dioxide? How many carbons and how many oxygen atoms would you have? You would say you have 2 of carbons for every 4 of oxygen, right? What if I said you had a dozen molecules of carbon dioxide? What would that be? How many carbons, how many atoms is that? You would automatically say, oh, there's 12 carbons and 24 oxygens, because this is a ratio of 1 to 2. This is double of this, right? So the same thing, so now we just take the next step and say, what if I have 1 mole of carbon dioxide? If I have 1 mole of carbon dioxide, how many moles of carbon do I have? You would have 1 mole of carbon. How many moles of oxygen would I have? You would have 2 moles of oxygen, right? So the subscripts then in a molecule will give us another conversion factor. And that conversion factor is, for example, in this one, for every 1 mole of CO2, we have 1 mole of carbon. Or the inverse, right? Okay, so let's do an example. And the problem says, how many moles of carbon is in 0.025 mole of aspirin? The formula for aspirin is C9H8O4. Okay, so we are asked to find how many carbon there are if you have 0.25 mole of the entire compound. Okay, so when you are asked that kind of question, you have to ask yourself, for every molecule of the compound, how many individual carbons there are, right? So you get a mole, you get a ratio from that, from the formula itself. So for every 1 mole of this, you have 9 moles of carbon. You will start by asking you what is the given, and the given is you have 0.25 moles of C9H8O4. Okay? You multiply that with a conversion factor between the molecules and the atoms. So for every 1 mole of C9H8O4, there are 9 moles, right? So you get the subscript is where you get that. 9 mole of carbon. Do that math, right? A reminder is that our unit analysis tells us it is properly set up because the moles of aspirin will cancel out with the moles of aspirin, giving you moles of carbon. Okay, so 0.25 times 9. If you do that on your calculator, what would you get? 0.25 times 9, you would get 2.25 moles of carbon. I know about sig figs though, since there's 2 sig figs here and 0 sig figs here, or infinite sig figs, because these don't count because they're exact number. You only rely on this number, so you have to have 2 sig figs. So to properly write this answer, you would say it's 2.3, because you have to round it up if only you'll have 2 sig figs. Okay, so let's do another example. In the same case, their next problem says how many moles of hydrogen you would have in 0.25 moles of aspirin. So again, the same thing here. We're asking to relate moles of an individual atom to moles of the whole molecule, right? So you start out with the same given, but the ratio is now different. Since we're not talking about carbon, we're talking about hydrogen here. What's the relationship between hydrogen and the whole molecule itself? For example, if there's 1 mole of the whole molecule, how many moles of hydrogen do you have? 8, right? So the ratio is 8 to 1. So again, these 2 units still cancel out, giving you moles of hydrogen, so you know that's how you set up the equation properly. Okay? So let's see what our answer comes out to be. 8 times 0.24, 8 times 0.25 should be 8 times 0.25, 2. Again, with 2 sig figs, that gives you 2.0 moles of hydrogen. Okay? Again, we can do that for oxygens too if we wanted to. Checkpoint. The question asks, how many moles of lactic acid, which is C3H6O3, contain 4.5 times 10 to the 24th atoms of oxygen? Okay. So to set up this question, you are given that you have 4.5 times 10 to the 24th oxygen atoms, and you need to find how many moles that relate to of lactic acid. Okay. So first of all, we know that we're given an amount of atoms, and we can't really use atoms or that kind of count very well until we have to convert to moles first, right? Because this is in terms of moles. So how do you convert from atoms to moles? Right, so let's start with saying that our given 4.5 times 10 to 24 oxygen atoms. So to go from atoms to moles, we would need Avogadro's number, right? So Avogadro's number says there are 6.02 times 10 to the 23rd oxygen atoms for every 1 mole of oxygen. Right? That's just the Avogadro's equality there. So from here, we see that oxygens and oxygens will cancel out the count itself. But we're asked to find the moles of lactic acid. So if you know moles of oxygen, what's the relationship between oxygen and lactic acid? Right? For every 1 lactic acid, there's 3 oxygens. So same thing with moles. For every 1 mole of lactic acid, there are 3 moles of oxygen. Okay, so doing cancellation here, moles of oxygen goes away with moles of oxygen, giving you moles of lactic acid at the end. Okay? So it's 4.5 times 10 to the 24th divided by 6.02 times 10 to the 23rd. That divided by 3 should give you 2.5 mole, or the answer B.